recording. Welcome everyone to the seminar. So today it's my pleasure to introduce Joe Bramante, who's joining us from Kingston in Canada. So Joe is faculty at Queen's University in Kingston, and he's just informed me that he's recently been tenured. So congratulations for that. So Joe is an expert on lots of things to do with dark matter. He's worked very widely on different aspects of dark matter and searches for dark matter. And today he's going to be telling us about a particular aspect of that, which I know is very interesting to a lot of people in the audience who are working on similar things. So Joe, do you want to share your screen and we can get started?
Yep, there's my screen, and I think everyone can hear me.
Yeah.
Just a question before I begin. Can you see my pointer on the screen here?
Yeah.
Okay, great.
Thanks.
All right, well, thanks very much for that introduction, Kieran. I'll take it from there. So yeah, today I'm going to talk to you about dark matter and compact stars. And at the end, I'm going to show you a little bit of a preliminary fun result with how dark matter actually could be affecting galactic structure. And it's not maybe the way you might expect if you know a lot about dark matter theories, where it would be self-interacting dark matter that I'd be talking about. It'll be a somewhat different kind of dark matter. And if you hear cats in the background, I have two wonderful young energetic cats named Wasabi and Paprika, who might be singing along with my talk right now. So hopefully I can introduce them so that you can get a face to that voice a little bit later. But I'll begin. Before I begin, let me just say, first of all, we like to give a land acknowledgement at Queen's University, so I'm going to do that. So I'm very grateful to be living, learning, and making friends, and coming to understand nature better on the lands of the Haudenosaunee and Anishinaabe peoples, which is where Queen's University and where I currently reside here in Kingston, Ontario. And another thing I want to say is during my talk, I'm going to be going through quite a few different dark matter and compact stars concepts, quite a few different dynamical processes. And so if you have a question about any particular part of what I'm talking about, feel free to speak up or even speak up in chat. I have both the video and the audio open, and I also have my little chat box open. So hopefully I'll see if anyone has any questions, either they voice or they write in the little chat box, and I'll try to respond to that as I go along. But yeah, feel free to jump in. All right. So today I'll take you through three main topics. The first one will be dark matter heating neutron stars through either infall or annihilation. So this will be a sort of new way that we've been trying to build up to look for dark matter. The second one will be a bit of an older topic that actually dates back to 1989 in its first incarnation, and that is that asymmetric dark matter can cause neutron stars to implode. And there are connections here to possible signatures related to missing pulsars in the galactic center and even fast radio bursts. And then the last topic I'll cover are white dwarf explosions from asymmetric dark matter or composite dark matter, and connections between that and type 1a supernovae and galactic structure. All right, so let me get started. So a fun way to think about neutron stars is as nature's dark matter accelerators, because that's literally what they are. So if we think about what makes detecting dark matter with the neutron star kind of special, the main thing I would emphasize is that neutron stars accelerate dark matter to beyond even the speed you'd expect dark matter to have when it's freezing out of the thermal bath, which is pretty cool. So particularly it accelerates dark matter to 0.7 times the speed of light. The next thing is that neutron stars are very dense, and as a consequence of that, they accept a very large flux of dark matter. So if I think about what sort of cross-section I would need to have with a neutron in order to hit at least one neutron as I'm moving through a neutron star, the parametrics of that are pretty simple. I can think about the radius squared of the neutron star as to get a sense of its area, and divide that by the number of neutrons. And because the radius of the neutron star is about 10 kilometers or 10 to the 6 centimeters, if I square that, I'll get 10 to the 12 centimeters squared. And if I divide that by the number of neutrons in a neutron star, well, that's a solar mass roughly worth of neutrons, which is going to be 10 to the 57 GeV, or 10 to the 57 neutrons. And so if I divide 10 to the 12 by 10 to the 57, I get 10 to the minus 45 centimeters squared as this sort of rough cross-section where I would hit at least one neutron if I move through a neutron star. And you can compare that with other astrophysical bodies like the sun or white dwarf, and that number is substantially lower, like 10 to the minus 39 or 10 to the minus 36 centimeters squared, after you do all the math and put all the spin-independent or spin-dependent form factors in correctly. And so this makes neutron stars pretty good dark matter detectors. And something we've been looking at for well over actually a decade, but we, in a study I put out with some collaborators in 2017, we're thinking about particularly that we don't have to rely on dark matter annihilation, but the signature we've been thinking about is that dark matter can essentially just heat up the neutron star. So I can think about dark matter accelerated to 0.7 times the speed of light. And even without thinking about any of its other properties, if it hits the neutron star, then just the kinetic energy it will have, because it's been accelerated to 0.7 times the speed of light, is enough to heat up the neutron star to something on the order of 1750 Kelvin for a typical dark matter density that I'd expect around Earth. If the dark matter also annihilates in the neutron star, this heats it up to 2500 Kelvin. And so the process here, which I've shown in a little cartoon, is that the dark matter is captured. Then the dark matter goes through some process where after it's hit the neutron star once, it's on an orbit where it'll hit it more and more and more, and it'll get a tighter and tighter orbit and heat up the neutron star. And if it annihilates, it could heat it up to about 2500 Kelvin. If it doesn't annihilate, it would be about 1750 Kelvin. And I can compare this to the sort of late stage temperature of a neutron star. And it turns out that a late term neutron star would have a temperature more around like 100 Kelvin. And yeah, we could get into why that temperature is below what you typically expect for a late stage white dwarf. And I'll leave that open to questions or comments in the chat. But that's about what you'd expect after a billion years for a neutron star. Okay. And so that's a temperature much below this temperature. And so I can then ask, what's the sort of sensitivity in my standard dark matter per nucleon scattering cross-section versus mass parameter space? And if I were capable of resolving the temperature of the surface of a neutron star to about 1750 Kelvin, this is roughly, and very roughly I should say, what the parameter space would be that I would be sensitive to in terms of the spin-independent or spin-dependent nucleon scattering cross-section, where really either one of those would fall pretty close to this blue line. That being because I'm not actually so beholden to think about a huge difference between spin-independent and spin-dependent if I'm scattering against individual nucleons, which I would be in this case. And I should note that, you know, these lines that I'm labeling here showing you what the temperature the dark matter would heat the neutron star to at this cross-section and this cross-section would be a bit higher if the dark matter annihilated after it was captured. Okay, so that brings me to the end of my flash introduction to dark matter kinetically or annihilation heating neutron stars. And the next thing I want to say is that immediately tell you that this field, since, you know, and before sort of that idea and that paper is much broader. So there are a lot of ideas coming from a lot of different authors in the mid-2000s about dark matter annihilation, maybe how you would see with X-rays or gamma rays towards the galactic center, what sort of the heating would be. Since then, a lot of authors have jumped in and done some really great work talking about exactly what the equation of state of the neutron star, what nucleon form factors under some different assumptions about the internal composition of the neutron star would do to change these sorts of estimates, either somewhat lessening the cross-section or in some cases somewhat increasing the cross-section sensitivity. One of those authors on some papers has been me. But it would take me a while to go through all the literature that's come out since then. I should say that there's been a lot of a sense of that this provides good sensitivity to a lot of different dark matter scenarios. Probably the main reason for that is that it's really hard to play the typical games you play where dark matter has a certain interaction cross-section at freeze out, or a certain interaction cross-section with certain kinds of standard model particles that doesn't show up in the neutron star. And that's because the dark matter is accelerated to quite a high speed. So it has sort of a kinetic energy to associate with freeze out on the one hand. And on the other hand, neutron stars are really interesting. They actually have a substantial muon component because their chemical potential is in the hundreds of MeV range. And that means muons actually are, flying around as, on-shell states in the neutron star C. In small fraction, but nevertheless they're there. And that means that even if you made some sort of a dark matter model that coupled predominantly through an L mu minus L tau current, so coupled to muon minus tau lepton number, you'd still be dealing with something where you can see that, and that there's a substantial scattering cross-section for that model with muons that would be in the neutron star. And so you wouldn't even need to go to loop level to see the interactions of that kind of model with the neutron star. And the last thing I'll mention, and I'll get back to in the second part of my talk, is that asymmetric dark matter has been studied inside neutron stars for a while by myself and other authors. And then all the way back really to 1989 by Isaac Goldman and Shmuel Musonov, who saw that asymmetric dark matter can actually turn neutron stars into black holes. And we'll get to there in a little bit. But before I get to there, let me say, okay, so what would it take now to find this neutron star dark matter kinetic or annihilation heating scenario? And there we perhaps have a ways to go. Here on this plot, what I'm showing you is what's actually a pretty up-to-date accounting of all the neutron star temperatures we've measured so far, log T in Kelvin on the y-axis, and log age in years on the x-axis. And so I haven't even shown you something that goes down to 100 Kelvin like I promised you it does, but it does. If you follow these cooling curves all the way down, you'd find that they go down to about 100 Kelvin after a gigayear. And really the scaling law pretty much kicks in and works at about 50 million or 100 million years at the latest, and probably more like at 10 million years. Because the sort of the heat capacity of the neutron star becomes very simple once it's just emitting photons below a certain temperature. This here for a while was the coldest neutron star seen yet, which is 10 to the 5 Kelvin, which is a far cry from the 2 times 10 to the 3 Kelvin that I was quoting a few slides ago, which is sort of the level you need to image neutron stars at in order to be sensitive to dark matter kinetically heating them if they're just hanging around in the halo. Since this came out actually, or since we first started looking into this, I should say, in 2018, a group went and used Hubble Space Telescope observations to dramatically decrease sort of the highest temperature bound that had been seen from a few times 10 to the 5 Kelvin to a few times 10 to the 4 Kelvin, which is a big step and makes it seem like, we can just, make the next step without much trouble, but actually the next step is probably going to be much harder. I'll talk about this neutron star a little bit. There is something dark matter related you can say about this with respect to kinetic and annihilation heating, but it's very specific, and I'll tell you about that in a little bit. Before I go there and say like what we can do right now with the coldest neutron star we've seen with respect to dark sectors, what I'll touch on is 30-meter telescopes and what they could do sometime in the future. So in our paper that we put out in 2017 and doing some calculations with some grad students in ongoing work since then, it seems somewhat realistic to think about neutron stars at 100 parsec distances, where these distances are all recorded from the ATNF pulsar catalog, but are something that you should really not take seriously, as we're finding out as we look more deeply into this. But something like a neutron star around 100 parsecs is a reasonable prospect. And then if I think about something like a 30-meter class telescope and what it would require to image a neutron star to the point that I could see both kinetic and annihilation heating in a certain amount of time at 2 sigma significance, it turns out I would need something like 3 times 10 to the 6 seconds, or about 1/10 of a year of observation time, which if you're not familiar with astronomical observation times is a huge observation time. I wasn't familiar with them. when I started looking into this. But it's not completely unreasonable in the sense that this sort of observation time has been allocated for things like Hubble Deep Field and other sorts of observations. So now I'm going to move a little bit beyond, something that we're building up towards, both in our understanding at an astrometric and at a basic theory level, and say, what could we do with sort of the coldest neutron star we've seen so far with respect to dark sectors? And something we can do is look for subhalo dark matter. And this is kind of a toy model for the kind of dark matter you might think about that can create substructure or a cosmological history that gave you subhalos. The subhalos I'll talk about for the next few slides are a kind of subhalo where you put all the dark matter into a subhalo with radius SH and mass M. And in order to talk about this, so far, all the numbers I've quoted to you have addressed the concept of collisionless dark matter, which is the kind of dark matter that isn't interacting with itself very much. But you could also consider in a scenario where the dark matter ended up in some sort of subhalo clumps of some size, that perhaps inside of that subhalo, it has an equation of state or interactions with itself that really make it quite collisional, so that its accretion rate onto a neutron star, instead of being collisionless, where the collection radius, as I like to think of it, or the sort of radius of the dark matter halo that the neutron star is sweeping out and is pulling into a trajectory that will intersect the neutron star, goes like v escape, where that's the escape velocity of dark matter at the surface of the neutron star, divided by VDM, where that's the velocity dispersion of the dark matter in the halo, times the neutron star radius. If you think about collisionless accretion, then there's a whole fluid matching derivation, fluid boundary condition matching derivation you have to do. And at the end of that, you find that the collection radius, instead of going like v escape over VDM, goes like v escape squared over VDM squared. And so that's in our galactic halo, an enhancement of the collection radius of about 10 to the 3, or an enhancement of the dark matter collected by up to a factor of 10 to the 6 after you square that, since we would think about an area of collection. And so I'm going to pause there if there are any questions about what kind of dark matter I'm then going to talk about for a few slides. So essentially the game that we played in a paper we put out a few years ago is we said, okay, so what might we say about like dark sectors right now using the coldest neutron star we've seen, which is that 10 to the 4 Kelvin neutron star I mentioned earlier. So myself, Nirmal Raj, and Bradley Kavanaugh got together and we said, well, if dark matter is in subhalos and it does have this character where it's accreting or falling onto the neutron star more like a fluid than a collisionless medium, which is a theory, by the way, we haven't built up from the ground, but is something like a dissipative dark sector that you might think about. That sort of dark sector we found actually you do have some sensitivity to, and we sort of charted out what you'd have sensitivity to in subhalo parameter space in the future. But before I move to the next step, if anyone has any questions up to this point and needs to get on board with what I mean when I say subhalo dark matter, certainly happy with that. Okay, so if everyone's happy, which I assume they are, then I'll move on to this plot. So what this plot is showing you is the parameter space then you have to think about if you want to think about subhalo dark matter that has some sort of per nucleon scattering cross section, here given in the typical mass versus per nucleon scattering cross section plane. And then up here in this plot, what I'm showing is the radius of the subhalo in centimeters versus its mass in solar masses. And so there are a number of pieces of this plot that I'll show you in a second. But before I do that, yeah, I'll note that up here, we would be looking at parameter space where the subhalos are not very dense, so the radius is bigger and their mass is lower. And in fact, their density could be so low that the subhalos we'd be talking about are just have a density that's lower than the galactic density. And so those probably just aren't very interesting subhalos at all, because they'd just be underdense with dark matter. So they wouldn't really affect collection or accretion in any substantial way. So it'd be like some sort of like it would be like some sort of perturbation to the density that's tiny. Okay. Then let's start tackling this. So I already said that this will be the subhalo parameter space up here that corresponds to your typical scattering cross-section versus mass parameter space down there. And essentially it's color-coded to show you what corresponds to what. So in pink, the region here, indicated by this pink arrow between this line and this line, we can use cosmic gray bounds, where these are the sorts of bounds where you take neutrino detectors or even underground dark matter detectors, and you say dark matter would upscatter, cosmic rays would upscatter dark matter so that the dark matter would hit those detectors at high velocities. And so you can set bounds on that kind of dark matter. And the point here is that even if you put all your dark matter into subhalos, cosmic rays can still hit it and propel it towards Earth. And you don't actually have much difference between what results you get there and your normal results for dark matter and subhalos. By the way, I definitely should have said this already. So you'll notice there aren't the typical xenon bounds or your typical dark matter bounds in this parameter space. And that's because for most of the subhalo parameter space we're interested in talking about here, the subhalo really wouldn't have passed through the Earth in hundreds of years. And so you have no guarantee that this sort of subhalo dark matter would have been seen at those detectors. Okay, so for these pink regions, so for this region here and corresponding to this pink region, you can rule out subhalo dark matter based on cosmic rays. Then for this region here, indicated by the brown arrow between this brown line and this dashed dotted line, you can rule out this using ancient mica. So if you take ancient mica or this dark matter search done in the mid-90s using a slab of mica, that mica sat around for 500 million years. So it isn't sort of limited in the way that our typical dark matter direct detection experiments are limited, in that they only have year to 10-year integration times. And so I can show that in this space, the subhalos would have intersected the mica over that 500 million years. And so you get the same number of events you'd expect from a WIMP in a typical non-subhalo dark matter setup. And so that's the sensitivity there. And then the sort of last little piece that I'll say is, I'm just going to skip to this one. In the special case that dark matter has some sort of a collisional bondy fluid like accretion onto the neutron star when the subhalo passes through it, you can actually already rule out this parameter space shown here, which is that same sort of bucket shape that I was showing you before. So you can actually rule out everything above here for the case of bondy accretion in this parameter space here. So if your subhalo parameters lie in this region, then that pulsar we talked about earlier, pulsar J2144, actually already sets a bound on the parameter space in a meaningful way. And so it's a very special model that you can use a nearby neutron star temperature to set a bound on currently. But it's just to show that there is something one can do with this at the moment already. Okay, so that's it for dark matter heating neutron stars and what the state of the art is with that at the moment and where we're sort of attempting to go.
Joe,
I'll pause there.
Can I ask a bit about these plots? So
yeah.
Are you assuming a particular density profile for these subhalos, like NFW or something?
Yeah, so yeah, we're being very toy model here. So it's a completely flat density profile. You could redo this and think about a NFW profile for each one of them. At the moment, I guess maybe motivated by the fact that we're thinking about this as a fluid, we felt like, okay, if it's a fluid, it would actually have something like a flat density profile because it would equilibrate. But yeah, yeah, it's a trivial profile at the moment.
What do you mean by flat? Like a just is it?
It's like a constant density profile.
Constant up to RSH or something.
Yeah,
okay.
Yeah, constant from R0 to RSH. Yeah, that's right.
Okay, so that's what allows you to draw these microlensing bands. I guess if you had a slightly smoother dense profile, you might not be able to do microlensing with them, or maybe it would be stronger. I'm not sure.
So Nirmal's actually the expert on this microlensing stuff. I think it's the case that for a lot of this microlensing stuff, it doesn't matter so much so long as the mass is concentrated within this radius, which isn't a very large radius, sort of what we're looking at here for the masses. So I'm not sure that the density profile actually matters too much down here, but yeah, for what we're doing, it certainly is going to make a difference. Yeah.
And so I think I missed what the relation between the top and the upper figure and the lower figure like is, because is this a sort of a three-dimensional parameter space where you have the cross section, the radius, and the mass, and you're just doing two slices through it or projection across it, or how does the lower panel relate?
Yeah,
I think I missed that.
Yeah. Let me try to do a better job then. So here, for instance, if I think about the region between this brown line and this brown line, this defines a region for a range of dark matter subhalo sizes and masses, right? So there's this whole region of dark matter subhalo radii and masses, all assumed to have a constant density throughout. Then what I'm saying is that in that region, I can rule out this portion of dark matter nucleon scattering cross-section versus mass parameter space. So this brown region is excluded for this region up here. Same thing for the cosmic rays. For this pink region down here, this region is excluded. And then what neutron stars can do is they can actually exclude everything above this solid line, but we didn't want to quite put it on exactly equal footing because this is a special case that it would be accreting like a fluid onto the neutron star. So we didn't quite decide to shade this in, but you could shade this in maybe in orange and say for Bondi accretion, this orange region would correspond to a constraint that essentially excludes all this parameter space here.
Yeah.
Yep. Okay. Thank you for asking. I think, yeah, this is it's 4 parameters actually, which is a lot. Yeah, we tried our best to make this understandable. Okay. Any other questions?
I just if you're going to move off of this topic, I want to quickly ask about the temperature of this neutron star, because you have this one this which I think you said was like an HST observation of this particular neutron star, but then you were talking about these like radio observations of the pulsars. Like they seem like they're two different measurements. Can you measure the temperature with like in the radio with pulsars? Because I would have thought you're more sort of probing the jet of the pulsar rather than the kind of the thermal temperature of it.
Yeah. So let me be clear then. The radio observations are all directed towards figuring out how far the pulsars are away from us and finding pulsar targets to then point optical or infrared telescopes at to do temperature measurements.
Oh, okay.
So we need to know where the pulsar is or where a neutron star is, and exactly how far away it is. Hopefully doing parallax measurements in radio, I would say, is the gold standard, before we then train our optical or infrared telescopes on it. So that's why I'm talking about radio here. What I'm saying is, like, we're trying to find a good target to send the optical or the infrared telescopes after. Yeah.
Is there anything you can tell about the age? Because you want to find like a really old neutron star, right? For it to be at a low temperature.
Oh yeah. So there are lots of different ways. Yeah. So there are lots of different ways to get after the age. Sorry, I'm just too excited. So the standard one is something called the characteristic age. So you actually take the period of the pulsar and you divide it by the change in time of the period of the pulsar, and this gives you what's called the characteristic age, which is a rough estimate which has its own caveats and provisos for the age of pulsars. Pretty much, it's actually more common for the pulsars to be as old as we need them to be, which is 15 million years or older, than for them to be younger, especially the ones that kind of we see out by us. But in any case, yeah, there's that for doing dating, and then if you need to, there are other methods you can use. You can use the age of a companion in a binary system, of which pulsars are often in a binary system. Yeah, there are other sorts of things you can say. That often people will just say millisecond pulsars should be really old because they've been respun, or at least that's some of the idea. But yeah, those are the main methods, and I would say P over P dot is the main thing. Yeah. Mm-hmm. Great. All right, thanks for the questions and clarifying that. Yeah, I think I went through that a bit fast, but very, very good. Thanks. All right. Yeah, I will move on to the next bit then. And I'm going to be a little pressed for time. I was perhaps too ambitious with everything I wanted to talk about. That's all right. So the next thing I'm going to talk about is asymmetric dark matter causing neutron stars to implode. And with every one of the sort of astrophysical things I'm going to talk about, I'm going to talk about, like, there are little signatures here that probably are just some other astrophysical thing. But if it turns out dark matter falls into the parameter space I'm about to talk about, then down the line we would say, oh, those things were the first glimmers of this. And the first thing I'll talk about a little bit in more detail is the idea that I kind of whisked through pretty quickly in the first part of my talk, which is that dark matter will thermalize in a compact star. And so let's talk about that a little bit carefully. So here I'm showing some figures that were actually made by a grad student at a PhD candidate at Queen's University, Narayani Tyagi, where we can think about, after dark matter is captured, it will undergo successive scatters that decrease its orbital radius. So each time it scatters, it'll deposit a little more energy into the neutron star, and it'll have a smaller and smaller radius. Until eventually, in something that's been called in the end in the literature T1 thermalization, I think actually Chris Kuvaris can be credited with coining this, the dark matter will end up fully ensconced within whatever object it's thermalizing with, in this case, a neutron star. So at sort of the exact moment that it goes from being captured to having an orbit that's completely inside the neutron star, this is the time period that's called T1 thermalization. But then there's a second period of thermalization, often called T2 thermalization, which is the time period for the dark matter to continue to lose energy until the dark matter particle has the same temperature as the neutron star. And often this results in a really, really tiny orbit inside the neutron star. And we'll talk about the parametrics of that in one moment, but I just want to point out that that's what's going on. That's what to keep in mind with respect to all this dark matter as it's captured and it accumulates into the neutron star. By the way, this is Wasabi, who's been creating lots of mischief and meowing a lot during my talk. It's very nice. Okay. So we talked about dark matter being captured, and the next thing we'll think about is when dark matter thermalizes. And when it's thermalizing inside the neutron star, a simple argument can convince you that the sort of trajectory it will be on is actually the trajectory you'd expect for a particle in a harmonic oscillator potential. In this case, it's a 3D harmonic oscillator potential. And that's related to the fact that it's actually in a constant density background. So that's roughly the parametrics of that. And when you think about the thermalization radius inside the neutron star, it turns out that you expect an extremely tiny radius, for instance, for PV mass dark matter of about 1 millimeter inside the neutron star for a neutron star temperature that isn't even that low, like 10 to the 5 Kelvin, which would be on the high end of these sorts of old neutron stars that we think about. Okay, so it's thermalized into this actually really tiny little space inside the neutron star. And you can think about, after you've collected enough of this dark matter inside the neutron star, it might begin to self-gravitate, or it might actually sort of exceed the density of the neutron star around it. And that's given by this condition here. And if that's the case, then you could think about whether at that point it would collapse. And there's a bit of a genes analysis you can do, but to well within a factor of 2 and more like 10 or 20%, if the dark matter has satisfied this condition, it's going to collapse inside the neutron star. It's going to lose energy actually by scattering with the neutron star as it collapses into a tighter and tighter ball. And then you need to figure out whether or not that little ball of dark matter would actually be able to form a black hole. And this would be the case if it can exceed its own Fermi degeneracy pressure. And it will do that if it has, if the mass of the fermions involved is around or greater than mass Planck cubed over mass of the dark matter squared. There's a quick derivation I would do for that if I were trying to go through a few different topics in this talk, but you can actually show on the back of an envelope why that's the scaling. By equating relativistic Fermi energy to the gravitational energy of a test particle, for instance, on the outside of that ball of fermions. And so this is one way to think about whether or not you can actually form a black hole out of the dark matter inside the neutron star. And that's one model to think about. The reason that we're thinking about heavier dark matter at the moment, and not something like GeV mass asymmetric dark fermions, is that if you sort of roughly sketch out how much dark matter you can collect into a neutron star in a galactic halo, after 10 billion years, even in the densest parts of our dark matter halos, you're not going to get much above 10 to the minus 12 solar masses. And in fact, you're only going to get that much if you're very close to the center of galactic halos. It'll be more like 10 to the minus 14 or 10 to the minus 15 solar masses out by us, and probably a little bit below that. And so what that means is just based on Fermi degeneracy pressure in the standard model, that GeV mass dark fermions in the standard model already, visible fermions in the standard model already can support a solar mass worth of weight, and certainly they can support less than that. And so you're not going to collect enough, and so that kind of model doesn't work. But what can work is either very heavy dark matter that's either bosonic or fermionic. And if it's bosonic, then it'll follow this relation. If it has a substantial self-coupling, where here lambda is its quartic self-coupling. And then another class of models I'm not going to talk about today that also works is you can think about bosonic dark matter, asymmetric dark matter that has a really tiny quartic self-coupling. So I did a little work on that as a grad student after a lot of people like Chris Kavaris, Peter Tennikov, Catherine Zurich, Haibo Yu, and Sam McDermott looked at some simpler cases than the ones I considered. And so that's another class of these models you can consider. It looks like we have a question. Go ahead.
Yeah, Joe, just to clarify about that one, the point is that it's got enough interaction to thermalize, but it doesn't have the right sort of interactions to hold itself up enough. Is that the point?
That's right. Yeah, right. So at the point that it thermalizes, and it exceeds the sort of density of the dark matter in that ball or that region exceeds the density of the neutron star.
Yep.
It can start collapsing.
Yeah, absolutely. No, I got that bit.
Okay. Yeah.
So
okay.
But the point with this special KeV to PeV range without the repulsive self-interaction. So it's they've got enough interaction to scatter, but they don't have a repulsive core term in the potential. That's the point.
That's right. Yeah. So there's even a paper by Nicole Bell, for instance, Calliope Petracchi, and another author whose name I'm forgetting, where they looked at what sort of a quartic self-interaction for these bosonic dark matter you would generate just based on thinking about it scattering with the nucleons. And there you have to be quite careful. But I think those authors would even agree that once you get up to these masses, it's not so important anymore, because I can put in an interaction that's order 1, or I can just say it's a fermion.
No, that part's
either
clear.
one of those. Yeah. Okay. Yeah. Great. Yeah. So here, there's a bit of a challenge. However, I've gotten pushback sort of in the other direction that I think is perfectly valid, which is that all of this that I'm talking about here assumes a positive quartic self-coupling, so it gives you a repulsive self-interaction, even though it will give you a sort of sick potential that has an unbounded minimum. It's possible to locally at least think about a negative quartic interaction for your bosons. And no one's done the model building towards that end and thought about neutron stars yet. By the way, anyone listening to this, feel free. And otherwise, eventually, maybe I'll get into it with some people. But you could go the other direction and say, what if I just generate a large negative quartic self-coupling? So I'm actually much better at collapsing. And then you can go that direction and see what happens. I don't think anyone's done that yet, actually. Yeah.
Okay, thank you.
Bro, thanks for the question. Okay, great. So sometimes I don't even talk about these other models because I find these models very simple and nice to think about. But yeah, there are lots of important things to think about once you think about, for instance, a bosonic model. So I'm not going to, for instance, talk about Bose-Einstein condensates, but that ends up being very important to thinking about how you form the black holes. They actually form most often out of a Bose-Einstein condensate when you think about these lower mass models. Okay. So then let's assume you form your black hole and it collapses. It's not supported either by repulsive self-interactions or Fermi degeneracy pressure. Then it will form a little black hole. And this black hole pretty much, well, in most of the cases, although you have to go do the calculation, for dark matter around 10 to the 7 or 10 to the 8 GeV, if it's formed a black hole, it's going to be big enough that it's going to then go on to consume the neutron star. But that's not a given. If the black hole formed is too tiny, which could happen for much more massive fermion masses, so you could form the black hole faster or with fewer fermions, it might be the case that it actually shrinks from Hawking radiation faster than it can grow through Bondi accretion, actually, of the neutron fluid around it. And in this case, it would actually just evaporate away. But assuming that it grows, it will consume the neutron star and you'll form a neutron star mass black hole. And that's pretty interesting. Okay. So immediately then, if I use an old pulsar in the Milky Way, and here, when I derived this bound, I used a pulsar that I could validate its age not only through the characteristic age that we talked about a little bit before, but also by using a white dwarf binary companion that had an age of a few billion years that matched the characteristic age of the pulsar. So I used both the radio pulsed metric for figuring out the neutron star age on top of a white dwarf companion's age. So I put those two things together and that makes you pretty confident that you got the age right. And so for like a 2 to 2.5, I think, around billion-year-old pulsar around us, this is roughly the bound you can set on really heavy dark matter. For dark matter masses below what we're showing here, it's difficult to, you can't collect enough dark matter to form the black hole in a few billion years. For dark matter masses above this mass, you'll form black holes, but they will actually be too tiny that you won't grow the black hole after it's formed, but it will start to evaporate. And so that's what we already talked about. So great. Okay, so this is all on the side of how do I put a bound on asymmetric dark matter, but you could ask, are there any sort of signatures or something that should make me maybe a tiny bit interested in this sector, because maybe there's something around that I could link to asymmetric dark matter imploding neutron stars. And there I would say, yes, there's this sort of missing pulsar problem at the galactic center, which was introduced by these astronomers Dexter and O'Leary in 2013. And so the missing pulsar problem, it's a little bit hard to explain it. And I had this plot that I showed, and it was always very confusing to both me and everyone I was talking to, mostly because I'm not an astronomer, so I'm not explaining it well. And so I started whiting out pieces of it, and then over time I just whited out the whole thing so that it didn't confuse anyone when I showed it. And so it's behind here, and I'll start revealing it now. Before I reveal it, I'll just tell you what's going on. So it turns out that when you're looking at radio pulses from the pulsar, there's this temporal pulse broadening, or the arrival time of the pulses will actually depend on the frequency of the pulses. And there will be a smearing in time of the arrival as a function of frequency because of electrons between you and where the pulses are coming from. And Raleigh scattering off of the electrons will essentially make higher frequency pulses show up later, and lower frequency pulses show up sooner. And so this effect can also, you can imagine, sort of smear out the pulses entirely and just make the whole thing indiscernible. And so based on what we thought was the column density at the center of our Milky Way galaxy of electrons, for a while we were thinking we're doing radio imaging of that central region, but we're not seeing anything. And that's okay, because we just expect there's a lot of electrons there. And so not seeing anything just means we have a huge electron screen that's removing our pulses. And so this plot I'm showing you now is from Dexter and O'Leary, and it shows you in terms of 1.4 gigahertz luminosity, and in terms of pulsar periods, what the sensitivity was of surveys prior to 2013 in both 5 gigahertz and 15 gigahertz to a population of of pulsars that had already been seen here, shown in blue. So none of these pulsars here shown in blue were seen in the galactic center. They were seen outside the galactic center, but it's just supposed to show you roughly in where in this parameter space these pulsars show up after you correct for this sort of dispersion measure piece. And so the 5 gigahertz and 15 gigahertz shows you the sensitivity if we have like this big density of electrons between us and the galactic center. For like astro-wonks, dispersion measure, I believe, is something like many thousands per centimeter cubed times parsec is the unit for the dispersion measure. Then we measured actually radio waves coming from the galactic center in 2013, and suddenly there is a problem because while here you could say, like, I'm not actually that sensitive to either millisecond pulsars out here or second period pulsars. I'm a little bit sensitive for some surveys, but not very sensitive yet. Once you actually measure radio pulses from the galactic center, you have a measurement of what the column density roughly is, and we weren't seeing the radio pulses that we expected to see. And so this led to the question, where are the galactic center pulsars? And you might be saying at this moment, oh, okay, Joe, this is 2013. We're now in 2023. So what's the state of affairs now? And actually, nothing much has changed, unfortunately. There have been many more surveys in the intervening period, specifically ones that finished off in 2021. And this is a more recent result from 2022. And there's increasing sensitivity to the population of pulsars we might expect to see in the galactic center. But so far, the only pulsar we've seen is an extremely bright, extremely young magnetar, which is pulsar J1745 2900. There are some other sort of neutron stars we've seen in the form of X-ray binaries and other things like that, but it's not the same class of objects and not what you're looking for when you're looking for pulsars. And just to be very specific, when I talk about the missing pulsar problem, because this leads to other questions and the relationship between this and the galactic center gamma ray excess, which people have talked about as being perhaps caused by pulsars. Feel free to ask me about that at the end. We'll have a few minutes left, I think. The region that we're talking about here is really the central 10 parsecs. And if you're orienting yourself towards when you normally talk about dark matter in the galactic center, you're probably thinking about like the galactic center gamma ray excess, and that extends over about a kiloparsec to roughly 3 kiloparsecs, depending on how you're doing it for the center of the galaxy. Okay, so then you could ask, what more can I do here? And I can think about how dark matter exists in the Milky Way, and whether or not, I can think about a dark matter model that would be removing pulsars from the center of the galaxy, and not be, not allow us to see old pulsars at the center of the galaxy because they essentially just turn into black holes. And of course, you can plot like a standard INASTO or an NFW profile and see what the dark matter density is at the center of galaxies. And you can particularly plot pulsar age curves. This is something that Tim Linden and I did in 2014. And what you can see is roughly what the maximum age of a pulsar should be based on dark matter accumulating in it and causing there to be a tiny black hole that then consumes the pulsar over the course of the lifetime of that pulsar. And this can give you a maximum pulsar age as a function of your dark matter parameters and scattering cross-section off of nucleons. And then you can plot all the sort of pulsars that have been discovered so far and their characteristic ages. And you can see that there's actually still quite a bit of wiggle room. This is actually a little bit of an older data set. Narayani, one of my grad students, actually recently plotted this, and this is filled in a little bit, but we actually haven't pushed into allowing ourselves to bound the parameter space based on galactic center pulsars. Yeah. The next thing I'll mention was not one of my ideas, but an idea of 2 astronomers around the time period that Tim Linden and I were thinking about this. It still hasn't gone away, and it's kind of an idea that we're still developing and thinking about. And that is that fast radio bursts might be linked to this as well. So fast radio bursts are these unexplained millisecond long radio pulses. They have a high rate and power output, and there are many applications for these that people are very excited about, including cosmological applications. It turns out that even before Fuller and Ott made this proposal, people had already thought about, what if we have a spontaneous neutron star collapse? Would that be enough to give us something that looks like a fast radio burst? And the answer to that, and the reason a lot of people connect FRBs to neutron stars, is the same. Yes, you can do that. And if you shed the magnetosphere of a neutron star, you can get something that looks like a fast radio burst. the time scale associated with that, roughly the light crossing time of the neutron star, being milliseconds, works out, as does the power and sort of the frequency you emit by shedding the entire magnetosphere dipole. You can then ask, can I actually implode enough neutron stars to account for the rate of some of the fast radio bursts we see? And the answer to that is yes. And so I did some work on that also with Tim Linden in 2017. And between these two dotted lines, what I'm showing you is a parameter space where you can have enough fast radio bursts occurring inside galaxies, Milky Way equivalent galaxies, to account for fast radio bursts. As a function of a parameter we started to define, which is sort of like integrated dark matter density times time that the neutron star is in the galaxy, which is a nice unit to use to just think about like how long it takes times how much density you need to implode the neutron star. So this x-axis essentially tells you what's the integrated amount of neutron star density around a neutron star I need in order to implode the neutron star. So any dark matter model that you come up with should predict one number for that. And so numbers lying between roughly 10 and 100, which actually this high mass dark matter range would also give you, would be able to give you a high rate of neutron star implosions and hence possibly fast radio bursts. Something I should mention is this definitely doesn't account for all fast radio bursts, because some fast radio bursts are called repeating fast radio bursts, although they have different spectral properties than non-repeating fast radio bursts, as far as we can tell so far. Repeating fast radio bursts probably shouldn't be caused by this, because this is probably a one-off thing. After you turn the neutron star into a black hole, you can't have more fast radio bursts because there's no magnetosphere left to shed. Okay. So that brings me close to the end of an hour and to the end of what I wanted to talk about mainly, which is dark matter kinetically heating neutron stars and dark matter captured inside neutron stars. And if it's asymmetric, so it can't annihilate with itself, enough can accumulate to form a black hole and then eat the neutron star. And here I've just shown you in terms of a broader dark matter parameter space where neutron star implosions sit in terms of probing dark matter. In terms of typical underground experiments, they're much more sensitive, but it is a sort of unique kind of dark matter. Although, you know, I would say it's not that wild. Okay, so with apologies, the last bit I'm going to go through a little bit quickly, but now that we've primed ourselves that, you know, I've set up dark matter accumulating in compact stars, I can actually explain the next piece pretty quickly. So the next piece we'll talk about is white dwarf explosions from asymmetric dark matter. I won't talk about composites. So type 1a supernovae erupt when you heat enough of the internal portions of a white dwarf so that you set off a nuclear chain reaction so that the heat from that chain reaction can feed more nuclear fusion. Then you blow apart the white dwarf, and in a successive amount of 56 nickel decaying to 56 cobalt decaying to iron, you get what we have come to know as these, you know, wonderful standard candles that we've used to find dark energy and many other fun things, which are these type 1a supernova light curves. It turns out that if you collect enough dark matter inside a white dwarf, and then it collapses in exactly the same way it would collect and collapse inside of a neutron star, this can also lead to the ignition of the white dwarf, because as the dark matter collapses, it sheds energy. And so you can show that it can shed enough energy actually to set off that chain reaction and cause the white dwarf to explode. Just as a quick note, more massive white dwarfs will be more compact and actually create more compact balls of dark matter. And less massive white dwarfs will have fluffier balls of dark matter that take a little bit longer to implode. So for a few reasons, actually, dark matter will cause, if you have a dark matter model that causes white dwarfs to explode by forming asymmetric balls that collapse in their interior, this will happen more rapidly with more massive white dwarfs. And so I had a paper in 2015 where I showed that you could reach the point of self-gravitation in sort of a heavy dark matter versus cross-section parameter space. And then you can ask that there be enough sort of collisions of the dark matter ball as it collapses to ignite the white dwarf, and that sort of set this parameter space region here. So I won't go over all the phenomenology of type 1A explosions, but I'll just say that there's a lot of investigation right now into what the progenitor actually is for a type 1A supernova. The leading astrophysical candidates are white dwarf mergers, or something that allows us to ignite lone white dwarfs, piconuclear reactions in the interior that we don't really have a full understanding of yet, or something like this is quite disfavored, so I hesitate to even say it, a helium shell on the surface of the white dwarf causing it to ignite. All of these are astrophysical options, but this is something else you could look for, and is one of those other sorts of glimmers of sort of dark matter phenomenology. And as before, you can also use these considerations and a lot of other fun processes. And this was work that I did with my grad student, Javier Acevedo, who's now a postdoc at SLAC, to put constraints on asymmetric dark matter. So here in yellow, I can show you the neutron star implosion bound, and then here sort of in orange, and a little bit in green, we have a bound on dark matter, which can implode and cause the white dwarf to turn into a black hole, but it can also ignite the white dwarf in a lot of different parameter space. Here, it's doing what I just told you. It's collapsing and causing it to ignite by injecting energy as it collapses. Here, it's actually forming a black hole after it collapses, but it's too small, so it evaporates. But that black hole evaporating then causes the white dwarf to explode. And this is the same dark matter mass versus cross-section parameter space. And so in my last minute or two, I'll talk about the second part of the title of my talk, which is that there could then be a connection between dark matter and the structure of galaxies, which is not self-interacting dark matter, but which would be something like heavy asymmetric dark matter or asymmetric dark matter that collapses inside white dwarfs. And I'll explain that now. So first, we have to briefly review baryonic feedback creating halo profile cores in galaxies. So this is work from Ponson and Governado, and essentially what they showed is if you have supernovae here in your galaxy that blow out the gas mass, this will cause a change in potential for your dark matter particles oscillating in that halo. And that change in potential can result in the dark matter being on a wider orbit when the gas blows out, because it's sort of lost the gravitational potential that was pinning it in. And then so long as the gas sort of collapses rapidly enough back to its original potential, then what you'll find is that you'll have a substantial number of the dark matter particles that you blew out staying blown out. And this is a way to change the inner density of your galaxies. And so they showed in simulations that have then been borne out in much more advanced simulations that have evolved over the last decade, to cause coring in low mass galaxies and even cause coring in higher mass galaxies. And then all the details of that are something that's fun and simulators are getting up to. But something we've been investigating over the last few years is whether dark matter could play a role in these feedback processes, and particularly whether asymmetric dark matter that causes white dwarfs to explode towards the center of these galaxies could create a kind of feedback or a kind of baryonic feedback that's a little bit different. And so one of the main, and I should say Yilda Buktuchin, a really great grad student here at Queens, has been definitely taking the lead on the simulation aspects of this. I can talk about what simulations we're doing and Gizmo if anyone's interested in that. So one thing I just want to note is there'd be a few interesting differences between standard baryonic feedback and dark baryonic feedback. So in the case of standard baryonic feedback, you'd have your supernova spread through the galaxy and blowing out the gas sort of in a sort of symmetric way where the amount of supernova sort of corresponds to star formation throughout the galaxy. For this dark matter induced white dwarf supernova or type 1A feedback, it would happen preferentially towards the center of the galaxy, which, so as far as we can tell, actually accentuates this sort of coring effect in galaxies. So far, we're still looking into this. We have simulations, but we want to do more. So it would maybe produce slightly different effects. So it would have a different location. And then it would be something that kind of shuts itself off because you'd be having these type 1As sort of at the centers of galaxies, removing dark matter or decreasing the central dark matter density. But that means that as you do that, you actually shut off dark matter inducing supernova at the center of the galaxy. So it would be sort of like a second nonlinearity on top of what's already a nonlinear mechanism that regulates star formation and cores galaxies, or rather the dark matter profile in galaxies. So here are some preliminary results that show you cumulative stellar mass formed. Here in dark blue, And for these two parameter space points, we see how much stellar mass would be formed in a small galaxy for 10 to the 8 GeV mass dark matter with these cross sections. But if I ramp the cross section up enough, then I will actually form fewer stars because I'll get this white dwarf feedback, essentially blowing out the gas at the center where I should be forming the most stars. And it turns out in those two cases, as compared to the case with just core collapse supernova feedback, which is the standard case, I would actually even see more coring in my galaxy than I would typically expect. This is something we're still looking into. So all of these results should be taken as quite preliminary. In fact, I should probably put a big preliminary stamp over these. Okay, so that brings me to the end of my talk. I went a little bit fast through the white dwarfs there, so feel free to bring that up in whatever question period time we have. So I talked about dark matter heating neutron stars, either through infall or annihilation. Asymmetric dark matter causing neutron stars to implode and connections to missing pulsars and FRBs. And white dwarf explosions from the same kind of asymmetric dark matter, and possible connections between that and type 1a supernova, and even as an extension of that galactic structure. So that's it, and thank you very much.
Great, thank you very much. Yeah, Roland, do you want to go ahead?
Yeah, thank you for the terrific inspirational talk, Joe. If I may, I've got two questions. One is that when you consider either the dark matter induced collapse of the neutron stars or the type 1a explosions, what about what does that imply for the radial distribution of those events in galaxies? Shouldn't that somehow reflect the underlying dark matter profile? And then, I mean, are the observations consistent with that? That's that was
yes, yeah, absolutely. So what you should see is there should be, and let me just check really quickly. Yeah, so we did a lot of studies in the 2017 paper to start thinking about measuring populations of neutron stars and white dwarfs in galaxies and seeing if we can see like a radial distribution that tracks the dark matter distribution, right? Because that's obviously something you should see in the end. Tim Linden and his collaborators actually have a recent paper out, Yuri Smirnov and some grad students, where they look at the distribution, for instance, of white dwarf explosions in certain classes of dwarf galaxies as a means to get towards that. Everything I would say so far doesn't present a hard bound beyond what I've shown you based on that distribution. But it's a little bit difficult because one thing you'd really like to know is, for instance, what's the exact dust and gas concentration towards the center of these galaxies? Because that can sort of create a bias where you already see like type 1As or fast radio bursts, mostly on sort of the fringes of the galaxies, just based on the fact that they're occluded towards the centers of the galaxies. And so we're actually working towards some projects where we would like to do better with mapping some tracers of neutron star distributions and type 1A distributions in galaxies, but we have to do that on top of trying to understand as best we can how to model what we won't see based on there being a lot of junk at the centers of galaxies. So yes, definitely what you're talking about is something we're trying to get into. Right now, the best galaxy we've come to understand is our own. And so these are all pulsars we've seen in our galaxy with their characteristic ages. There are some that we've seen a little bit closer in with a little bit larger of a characteristic age. One thing you would want to do, though, before you even took one of those and try to set a new bound on asymmetric dark matter using it, is really carefully study where it sits and whether it actually is this close to the galactic center. Because everything I'm showing you here takes a distance from dispersion measure distances. And it turns out you need to be very careful with those because there are estimates based on an imperfect map of electron density in our galaxy. And so you can very easily over or underestimate those as well. So yeah, I'm really super interested in pushing forward either observation or bounds on this parameter space. But yeah, there are some additional things that we're contending with, mostly related to our basic understanding of what both the neutron star distribution, the free electron distribution, dust and gas distribution should be in a typical galaxy, and then how to take data sets and sort of slap all that together.
Thank you very much. I don't know whether I did have another question if there are no other questions.
Yeah, go ahead.
Well, this is kind of an idle question, but you were just mentioning for a part of the dark matter, mass cross-section parameter space, the black holes that you predict to form inside the, right in the centers of the neutron stars are too small, and then they Hawking evaporate before they can grow. But I mean that in principle is some sort of heating, right? So is that any sort of interesting constraint, the Hawking radiation from those evaporating black holes in that part of the parameter space?
Yeah, so as far as I can tell, that means that the sort of all the things I said about annihilation heating actually do apply to all the parameter space lying above here. Because as you just pointed out, these black hole, so if I form an evaporating black hole, fine, that still deposits energy into the neutron star. None of that should escape as anything more than thermal energy based on the cross sections of every standard model particle we know, for temperatures that will be at first, somewhat low, but at the end, extremely high. And so, yeah, unfortunately, I wish there was something like a neutrino signature I could think about here. But yeah, even neutrinos at sort of any temperature above hundreds of MeV aren't even going to make it out of the neutron star. They're just going to get sort of absorbed mostly, and then that's just going to be thermal energy. So if you want to stack a BSM scenario on top of a BSM scenario, you could say the sort of any extra degrees of freedom that are that the neutron star is optically thin to, that the black hole evaporates to. Maybe you can search for that in the parameter space above here. But just the black holes themselves, here, it's still a good point that you'll then heat the neutron stars to these temperatures we would think about for annihilating dark matter, even though this isn't annihilating dark matter parameter space. Yeah.
Yeah. Thank you. Cheers.
Thanks.
All right. Is there anyone else who wants to go before we wrap up? I think that's exhausted all the questions. So yeah, thanks again, Joe, for the really interesting talk. So yeah, well, let me stop the recording.